Hello, my name is Mark Whalley and I'm Education Manager at the Institute of Physics. In this video, continuing in our IOP domain series, we're going to be looking at advanced force diagrams and using vectors. This video is for anybody who teaches forces to students aged 14 and upwards, and it will develop the material that we've already presented to you in our other videos on force arrows and on Newton's second law. Over the course of this video, we're going to look at several things. We'll start off by considering why vectors are important and reflecting on some of the challenges involved in teaching vectors. And then we're going to look in a lot more detail at coplanar equilibrium, balanced forces in more than one dimension. And the way we're going to do this, we're going to focus on the inclined plane. We'll look at an experiment you can do, then we'll have an in-depth look at the theory behind it. But just to start off with, let's consider why vectors are important. I often feel that when dealing with challenging new material with students, it is important to actually explain to them why we need to use it. It ensures, or at least it helps with engagement. So why are vectors important? Well, unlike just dealing with simple numbers, vectors have inherent within them direction as well as magnitude, and so they can be used to describe so many more quantities than simply scalar quantities can do. So for instance, if we're dealing with a system where a certain variable depends both on its position in more than one dimension and on time, a vector is ideal for doing so. Projectile motion is a great example of this, where we've got X and Y motion, and obviously anything to do with motion involves time as a variable. And beyond post-16 in schools, vectors are such an important part of both physics and engineering, which we hope that many students that you teach will pursue. So let's just discuss a couple of the challenges that both students and teachers may face when dealing with vectors. Many of our students aren't taking A-level maths, and consequently vectors can be an entirely new form of mathematics to them. Whilst at GCSE they may encounter them in a graphical form, a more analytical form is only encountered at post-16. The great thing, of course, about vectors is they possess both magnitude and direction, but a conceptual element that makes them quite challenging is the fact that they are movable, that as long as magnitude and direction are conserved, we can move vectors around, which for some that may be a challenge, but when we're confident in our use of vectors, it's also a true blessing. There's another peculiar aspect of vectors, and that we are representing often graphically quite abstract quantities. So for instance, if we're representing a force as a vector diagram, there we have a physical length on a piece of paper actually representing something that doesn't possess those dimensions. So now let's move on to the specific example of the inclined plane. You've met balanced forces before in Newton 2. But in that presentation, these were in one dimension, essentially in a system which is either at rest or in a state of uniform motion. The forces to the left equal the forces to the right, the forces up equal the forces down. But we're going to complicate matters now. And we can see here a person in a wheelchair on a slope. And the question is, if she's at rest, why doesn't she move? So let's start by thinking about what we know about the forces already acting on objects at rest. If an object's at rest, then in a particular direction, the forces need to be balanced. Now, in this example, things are already becoming a little bit more complicated, because if motion were to occur, it wouldn't just be up and down or left and right, it would be both of them. Moving down the ramp is both an up-down motion and a left-right motion. And we also know that when we get motion, we often get a force to oppose it. So let's have a think about what forces are acting on her and in what direction those forces are acting. We'll go beyond that, and we will also then look at how can three forces, all in different directions, actually be balanced at all. So the first force is weight, acting directly down. And that is always going to act down irrespective of the angle of the slope. Now, without the slope, this person would want to move downwards, and so there needs to be a force opposing that, and that is the support force. Now the support force is at right angles to the slope. But what about the other sort of motion that she might take? Well, not only would she move up and down, we mentioned earlier she would move left and right. And so there needs to be a force opposing that left-right motion, and that is, of course, friction. And again, friction will be along the direction of the slope, as that would be the direction of the motion. So how can we represent these in a slightly more physics-based way? So we tend to always remove the object, and we prefer to go for a free body diagram in which extended objects are represented by points at which all of the force arrows originate. So here we can see those three forces. We can see the weight acting vertically downwards. We can see the support force acting at right angles to the slope, and we can see friction acting up the slope. But of course, this raises a question. The force up doesn't quite look like the force down, and the force left and the force right, they don't look balanced. So what is the condition for equilibrium? And we've also seen in previous videos that the conditions for equilibrium are that we can rearrange the vectors to form a triangle. Coplanar vectors in 2 dimensions will be in equilibrium if, when they're moved around, they can form a triangle. So let's go beyond the graphic I've just used and see how we would actually graphically close that triangle. So let's look at an actual example, an idealized version of the situation we've already considered. Let's consider a triangle of forces where we've got a weight of 80 Newton, a support force of 69 Newton, friction 40 Newton acting up a ramp whose angle is 30 degrees to the horizontal. And we're going to draw this. So what we'll start off with doing is just drawing a set of axes. I'm quite conscious that because of the graph paper, the pencil line may not be particularly visible, but hopefully you can follow what I'm doing. So the first one I'm going to draw in is the 80 Newton, the weight, and I'm using a scale of 1 millimeter to 1 Newton. So my 80 Newton fits in nicely on that axis, and I will draw an arrow at the bottom of it to denote the end, and I'll mark that up in pen to say 80 Newton. Now our ramp is at an angle of 30 degrees, so placing the protractor on so that it's aligned with the horizontal and the vertical, I'm going to mark my 30. I'll draw a faint line from the origin through that, and then on that I will mark in a line of length 40 millimeters to represent our 40 Newton force. So that ends actually just there, and again we'll label those quantities that is 40 Newton, and we know that that's 30 degrees. And then finally we need to put the support force on. Now we know that the support force is at right angles to the slope, so it might actually be quite helpful just to extend the slope backwards, even though we know in reality the slope will stop when it reaches the horizontal. It just helps us with using the protractor. So let's place the protractor on there, and we want to mark off 90 degrees relative to the ramp because that's the direction in which the support force acts. And we will now draw that line in. There we go. And we want to mark off a force of length 69 millimeters to represent our 69 Newton. There we go, so that goes to about there. And again, we'll mark that up as 69 Newton. Now, what we need to do is move our vectors around. We're going to leave the 40 Newton where it is. That doesn't need to be moved. So what we're going to do, we're going to do 2 operations. We're going to move this 69 Newton vector in that direction. And then we're going to move the 80 Newton vector upwards. So firstly, we know that the 69 Newton vector, its direction is maintained, so it must still be at right angles to the slope. But we're going to move it to the end of the 40 Newton vector. So we go to the end of the 40 Newton vector, mark off 90 degrees. After all, it is at right angles. And we will then, may as well do all of these things together. There we are. Oh, just get that properly aligned. Now that's properly aligned. You can see I'm at 69 Newton there. There's my 90-degree mark. I draw my vector in. That is 69 Newton. And now I'm going to translate this vector upwards. It's 80 millimeters long, representing an 80 Newton vector. And that then completes a closed triangle just there. And just to illustrate that slightly more clearly, what I'm going to do is just go over that in a colour. So I will go for purple, and we can see there's our 40 Newton. Hopefully that's a little clearer for you. There's our 40 Newton. There's our 69 Newton. At right angles, that is a right angle just there. And the triangle is closed perfectly by 80 Newton. So now let's look at a practical activity that you can use quite simply in the classroom to actually illustrate what's going on in this situation. We looked at in the previous slide the idea of a closed triangle, but we want to think what actually happens as angles start changing. What happens as the inclination of the slope increases? Now, as long as the object remains at rest, that triangle must remain closed. Now, one side of that triangle will be unchanged, and that side is represented by the weight vector, the magnitude and the direction of which will be unchanged. But if the angle of the slope increases or decreases, then the direction of both the support force and the frictional force have to change. And so the only way to keep that triangle closed is the magnitude of both of those vectors has to change. Now, if we just consider one direction in particular, the direction in which the support force acts, i.e. at right angles to the slope, we also have to have equilibrium along that axis. So acting at right angles vertically away from the slope, we have the support force. Acting in the opposite direction, we have the component of the weight. So if the support force is changing to keep that triangle closed, the component of the weight in the opposite direction must also change. And here's a really simple way of showing that. What you'll need is a slope, something like a plank or a board, which you can raise at one end. Place on it a set of digital scales. For instance, kitchen scales are superb for this. And on top of the kitchen scales, place a weight. Experimentally, my tip would be secure everything as firmly as possible to both the plank and to the scales. You also need some way of measuring the angle of the slope. You might just want to go for a protractor, or you could use something like the Firefox app on a mobile phone, which allows you to measure inclination. So I'm going to hand over now to my colleague Daisy Fox, who's going to show you this experiment in action.
This is a really basic experiment to show how the component of weight is a function of the angle of an inclined plane. We'll just talk through the setup first. I've got a set of scales from the kitchen, so a set of digital scales to give me those that most accurate reading as possible. And above the scales you can see that I've got my phone, and I'm using the Firefox app on my phone to help me measure the inclination of the plane as I'm raising my board through all these different angles. and that's gaffer taped as well as the scales to the board to stop them slipping. You can also see I've got some bits of gaffer tape on the scales as well. They're obviously there to stop the masses from slipping as we go up through our different angles. Now, the masses I'm using are just ones that you would typically find in a school lab. I happen to have a set of these at home. So we're just going to fix these to the scales. And you'll notice that what I'm also trying to do, and I'm configuring them in such a way that tries to keep the centre of mass of the weights as low as possible. And that will help us get some really nice results that are close to that theoretical value. Now, it does mean, for those of you who are fussy about this like I am, I don't like doing this, but what it means is that I'm only putting 900 grams of mass on the scales because the mass hanger affects that centre of mass. So I've deliberately left them off, which means that I'm starting at around about 900 grams instead of around 1,000. But we'll go through the angles and see what the data throws out. So we need to well, first of all, I can't zero Firefox, unfortunately, so you can all see how wonky my floor is. The other thing we need to consider is just, as we raise the board, we just need to make sure that we're moving quite slowly so that we're giving the app time to respond as we're moving through all these different angles. So I've gone through 5 already. I'm just about to approach 10. There we go. Moving up to 15 now. Nearly at 20. 25. We're at 30. Nope, 30, there we are. 35. Oh, try and get that 35 reading really good. There we go. And stopping at 40. And there we are. So we'll pause there and have a look at the data.
So you can see from Daisy's experiment that as she increases the angle of the slope, that the weight as recorded on the kitchen scales clearly does go down. We've plotted that data here, and those are the black crosses. And you can see that as we increase the angle, the weight is definitely dropping. You'll also notice a blue line. The blue line is a theoretical prediction for what should happen to the weight. And the actual form of that line we're going to consider in a few minutes' time. We can't escape the fact that the experimental data and a theoretical model aren't the same, and that in itself makes for a good activity with your students to consider what the source of that is. But experience tells us that the more securely you can both attach the scales to the ramp and the weight to the scales, then those points get closer and closer to the theoretical model. So now what we're going to do is just have a look at the way in which the forces change as the slope changes angle. We'll look at two extremes to start with. Let's have the slope being completely horizontal. So here we've got the weight acting straight down, and that's going to be a vector that never changes both in terms of magnitude and direction. Now, for the forces to be balanced, there needs to be a support force which is of the same magnitude as the weight, and that acts vertically out of the plane. Friction doesn't matter because there's no way in which that object can move up and down the plane as it's horizontal. So now let's consider the extreme situation in which we start to incline the plane and we're going to reach a point where the plane is vertical. Now, I know this is stretching the imagination a little bit, but let us just imagine that in this case, we're almost on a vertical slope, and yet the object still doesn't move. So this time, we need friction to be of the same magnitude as the weight. But now, of course, the support force, if it was that big, the object would fly off the ramp. So we are going to just retract the support force, and now we have, again, balanced forces. However, for the types of problems we're looking at, more often than not, we're going to have the ramp at some intermediate angle. So let's return the ramp to somewhere in between. And consider what's happening with the forces there. So still, we've got a situation in which we need a support force. But this time, of course, we can clearly see that if we have a force acting up the slope of that magnitude, in fact, the object would move. This force is reactive against the motion of this object. The object wants to move down the slope, and the frictional force acts to oppose its motion. So now let's start attaching some maths to this and building up a description using trigonometry. The first thing we need to do is define our axes. So let's do that. In this case, we know that the frictional force and the support force are always at right angles to us. And the frictional force is along the slope, whilst the support force is at right angles. And so this gives us a natural place to draw our axes. So I'm just going to draw that on here. So this is going to be our x-axis. And we'll draw the y-axis at right angles to it. And so now let's add on our key forces. The weight, which acts from the middle of the object, and we're not actually doing a free body diagram here because I am using an extended object for the weight, will act from the center of the object straight down. I'll label that W. The support force is along the y-axis. So I'll go over the top of the axis to draw that. And that is our support force, which I will label S. And our frictional force is going to be heading up the y-axis from the object. And I'll label that F. One thing that we do need to look at before we go any further are issues around angles. You'll notice that we've got angle theta here. But actually, the angle we really need to know is this angle. If this is theta, then what we have is a right-angled triangle here. Since that's 90 degrees, this becomes 90 minus theta. But we've also got a right angle there. So if that's 90 minus theta, this must also be theta. Now that we've defined the x-axis and the y-axis where we can actually see that on this diagram, the weight lies along neither of them. So there's going to be some component of weight acting along the slope and some component of weight acting into the slope. And so our next step requires us to work out what those components are. Now, the way to do it is to draw in some triangles. And what we want to do is from the end of the weight force arrow is to draw an angle which crosses the y-axis at right angles. Now, there is a misconception here, and some students would be tempted to draw the line here. But don't forget, everything can be moved around. And so just for convenience, I'm going to twist the entire diagram around so that now my y-axis is horizontal. And then we can see quite naturally a right-angled triangle forming here. So I'm going to draw in that line there. And that allows me to define a component of weight along that axis, which I'm going to draw just here. There we are. Similarly, I can draw in the component of weight along the x-axis. There we go. And I shall draw that in there. Now, we may as well continue whilst this is in this orientation. We have a right-angled triangle. We have a hypotenuse of magnitude W, and we have an angle theta. In this right-angled triangle then, the cosine of that angle equals the adjacent over the hypotenuse. This triangle, on the other hand, rather than this length being dependent upon the cosine of the angle, it will be dependent upon the sine of the angle. And so just using basic trigonometry, writing that cos theta is the adjacent side, and we'll actually call that WY, because it's the component of weight along the y-axis, is the adjacent WY divided by the hypotenuse W, and that therefore gives us that WY, the component of weight along the y-axis, is W times the cosine of the angle. Similarly, over here, we will call this WX, and without any loss of generality, we can say that WX will be W sine theta. So now we're in a position to actually write down the relationships which we will need to solve a problem. We'll consider two directions. We'll do the analysis along the x-axis, we'll do the analysis along the y-axis. Since the object is at rest, the forces along the x-axis must be balanced, the forces along the y-axis must be balanced. And so what we will simply do is this. We will notice that the forces going up the slope must equal the forces going down the slope. There we go. They must be the same. So let's write that down. We can write that the friction must equal W sine theta. And in addition, the forces going at right angles to the slope upwards must equal the forces at right angles to the slope going downwards. So these forces must be equal. The support force S must equal the component of weight at right angles to the slope, and consequently S must equal W cos theta. It's likely that in any situation, students will be expected to find something like the magnitude of the frictional force and the magnitude of the support force, having been given the weight of the object, or at least the mass and the gravitational field strength, and the angle of the slope. And so to finish off, let's do a quick worked example. And here we go. An object of weight 80 Newton rests on a slope at 30 degrees to the horizontal. Calculate the frictional and support forces. So we've already set up the algebraic description in these two equations. If we go for the frictional force first, remember what's happening. The forces going up the slope equal the forces going down. And so F equals W sine theta, which is, well, W, we've been told in the question, is 80 Newton, times the sine of 30. Sine 30 is one of those important trig facts that most A-level students should know, and that is 0.5, which gives us a component of 40 Newton. That is the frictional force. Now let's move on and just work out the support force. S is W cos theta, which is 80 times cos 30, which is 80 times 0.866, which gives us an answer to 1 decimal point of 69.3 Newton. Thanks for joining us in watching this video on forces. We hope you found it useful. Please also have a look, if you haven't already done so, at the other videos that we've got covering the forces domain. You can find out more about the domain's CPD program on Talk Physics, where you'll find details of our interactive sessions and future provision. Thank you once again for joining us.